Hi, in this video, we are going to look at Diophantine equations, and this is part 2 of the earlier video that we made on this topic. So we are going to look at some more problems and some advanced concepts for indeterminate equations, and that will conclude our section on number theory for the course. So let's get started. The first question is this: prove that the equation x plus 1 power y minus x power z equal to 1, where x, y, and z are greater than 1, has only one group of positive integer solutions, positive integer solutions, where x is equal to 2, y is equal to 2, and z is equal to 3. Basically, we have to show that this equation has only one solution. X should be 2, y should be 2, and z should be 3, right? Okay. So let's start by looking at the equation and take the equation modulo x plus 1. We are taking modulo x plus 1 in the equation. So obviously this is 0 mod x plus 1. And if you think about it, x power z is equal to minus 1 power z modulo x plus 1. So mod of x plus 1. So we have overall minus 1 power z minus mod x plus 1 is the same as 1 mod x plus 1. On the two sides, this is what we get. So this is minus 1 power z plus 1 mod x plus 1 is the same as 1 mod x plus 1. And from here, we can basically reduce that since this is becoming 1, z plus 1 must be even. Z plus 1 is even, so z must be odd. So taking the equation modulo x plus 1, we can conclude that z must be odd. Okay, so that is the first thing that we have figured out. The next thing is this. Our equation is x plus 1 power y minus x power z equal to 1. And now we can write it as x plus 1 power y is equal to x power z plus 1. And we have already figured out that z is odd. So since z is odd, we can factorize this like x plus 1 times x power z minus 1 minus x power z minus 2 plus alternating signs in this factor minus x plus 1. This is what we get factor after factorizing. So obviously we can cancel one factor here. We'll get x plus 1 power y minus 1 is equal to x power z minus 1 minus x power z minus 2. These factors, this is the expression that we end up with, right? Now, if you think about this, this is an odd number of terms, because the z minus 1 is even. So it is something like this, x square minus x plus 1. It will be 3 terms if z was 2, if z was 3, right? So this is an odd number of terms. And if x is odd, then the RHS will become an odd number of odd terms, odd number of odd integers, right? So that implies that RHS will be odd in that case. However, LHS, if x is odd, x plus 1 is even, so LHS is even, which will be a contradiction. So x cannot be odd, So therefore, x must be even. So far what we have figured out is z is odd and x must be even, right? Okay. The third part of the question that we can say is we have this equation x plus 1 power y minus x power z equal to 1, and we can rewrite this as x plus 1 power y minus 1 is equal to x power z, right? Once we have rewritten it like this, we can use the factorization of x power n minus y power n, which is x minus y and x power n minus 1 plus so on, x power n minus 2y and so on, right? So I'm going to use that factorization here, and I'm going to rewrite this as x plus 1 minus 1, and inside the bracket I have x plus 1 power y minus 1 plus x plus 1 power y minus 2 and so on till x plus 1 plus 1, which is equal to x power z. Now think about it. This term is equal to x, so we can cancel one factor here. So we get basically x plus 1 power y minus 1 plus x plus 1 power y minus 2, so on till x plus 1 plus 1 is equal to x power z minus 1, right? Now we know already that x is even and z is odd. This is stuff that we already know. So if x is even, x plus 1 is odd, and this is also odd. All the terms here are odd, right? All the terms here are odd, but this side we have an even number, because x power even power something will be even, right? So how will we get the sum of odd numbers to be even? The only way for that to happen is if we have an even number of odd terms. It must be an even number of odd terms. And how can this be an even number of terms? The number of terms here is actually y. So then that means y must be even. The number of terms here goes from power 0 to power y minus 1. So number of terms is y. So y must be even, right? So throughout this question so far, just by looking at the different parities of all the powers, we have been able to, after a little bit of manipulation and factorization, figure out these three things, that x is even, z is odd, and y must be even, right? Correct. So now we go towards the solution and we write let x be equal to 2x1 because x was even, and y is equal to 2y1 because y was also even, right? So look at the original equation, x plus 1 power y minus x power z equal to 1. This equation can now be rewritten as x plus 1 power 2y1 minus 1 is equal to x power z, right? And this can be factorized now as x plus 1 power y1 plus 1 multiplied by x plus 1 power y1 minus 1 is equal to x power z, right? Now we know that x is even, so these two numbers, it is clear that these two numbers are different. The difference between the two numbers is simply 2, right? And x plus 1 is odd, and we can say that odd number some power, this whole thing is odd, odd plus 1, this is even, and this is also odd minus 1, this is also even, right? So it is clear that the GCD, greatest common divisor, of x plus 1 power y1 plus 1 and x plus 1 power y1 minus 1 is 2. Why is it obvious? Because the numbers are something like this, n and n minus 2, where both of them are even. This number is even, this number is even. So obviously 2 is a common factor, right? So GCD of these two numbers will be 2. Okay. So also we know that x divides x plus 1 power y1 minus 1. How do we know this? Because x can be written as x plus 1 minus 1. And we know that the factorization of this can be written as x plus 1 minus 1 and then x plus 1 power y1 minus 1 and so on, right? So clearly x is a factor of this. So we know that x divides the smaller number, x divides this, and also both of them have GCD of 2, right? Correct. And let's rewrite the main equation here. We have x plus 1 power y1 minus 1 multiplied by x plus 1 power y1 plus 1 is equal to x bar z, and x bar z can be written as x can be written as 2x1 whole power z. So you have 2 power z x1 power z, right? So the product of these two numbers is this, and GCD of the numbers is 2, and x divides x plus 1 power y1 minus 1, right? X divides x plus 1 minus y1 power 1. So basically you have 2x1 divides this, right? So from here, you can easily conclude that I can call this number as 2x1 power z, and I can call this number as 2 power z minus 1. If you choose these two options, what will happen? You can clearly see that the GCD of the numbers will be 2, and also 2x1 will divide this, right? If you put any x1 term here, what will happen is GCD will become bigger than 2, it will become x. That is not the case here. So overall, what we are getting is x plus 1 power y1 minus 1 should be equal to 2x1 power z, and x plus 1 power y1 plus 1 should be equal to 2 power z minus 1, right? Correct. Now we have xyz should be greater than 1. The only possible way in which this can happen is if you have the solutions 2, 2, and 3 for x, y, and z. Because in that case, if you take x as 2, y as 2, and z as 3, 2x1, x was 2x1, so x1 means is becoming 1 here, right? And y1 is also 1. So if x1 is 1, we'll get this part here as 2, and this part here as 2 power z minus 1, which is 2 power 2, 4, right? So you have the product of these two is equal to 2 into 4. That fits the x power z. So you can clearly see that this is the solution. This is coming as a solution. And that is going to be the only possible solution, because we need to satisfy these conditions. X should divide this, right? X plus 1 power y1 minus 1. So 2 divides 2. That is correct. If you try to take a bigger solution, you will not be able to satisfy this condition, which you can verify. You can basically try and plug in some higher solution, and you will fail to satisfy the condition that the GCD of the two numbers is 2. The GCD of the two numbers is 2 means one of the numbers, both the numbers are even, but they don't have higher powers of 2, right? I'll leave that final step for you. Try it out. Hopefully, you will get the idea here. The next question is this one. Prove that if the equation x square plus y square plus 1 is equal to xyz has positive integer solutions, has positive integer solutions x, y, and z, then z is equal to 3. Okay, so we are going to approach this question by a proof by contradiction, and we are going to say that if there is a positive integer, if there is a positive integer z not equal to 3 such that the equation has a positive integer solution x, y, and z, then x cannot be equal to y. So first I will establish that x cannot be equal to y if there is a positive integer solution z which is not equal to 3. How? So we will say if x is equal to y and z is not equal to 3 is a solution of the equation, then we get simplifying the equation, x is equal to y, so equation becomes like this: 2x square plus 1 is equal to x square z, and from here we can say that x square into 2 minus z is equal to minus 1, right? X square into 2 minus z is minus 1, so x square is positive, so this must be negative, and if this is negative, then that means z is less than 2. And if z is less than 2, z can be 1, 0, minus 1. If it is minus 1, what will happen? Right. Actually, it cannot be minus 1 because z is supposed to be a positive integer solution. So the only option for z is 1, right? So if z is 1, what happens? No, I am making a mistake here. We are getting this equation. So from here we know 2 minus z should be less than 0. So z should be greater than 2, obviously. So if z is greater than 2, z can be 3. If z is equal to 3, you will get minus 1 and x is equal to 1. If z is 4, however, you would get minus 2x square is equal to minus 1 and x square is equal to half. So that will not have integer solutions after that, right? So the only option from here is z is equal to 3 and x and y equal to 1. So basically what we are getting is a contradiction, because if x is equal to y, you are getting z is equal to 3. But we are supposed to take the case that z is not equal to 3, right? So what we are saying basically here is that if z is not equal to 3, then x cannot be equal to y. X cannot be equal to y, right? So since x and y are symmetric in the equation, there is no difference between the variables x and y. We can assume without loss of generality that x greater than y. X is greater than y, right? Now what we will do is we'll do a proof by infinite descent, the idea of infinite descent. So we'll say select a solution x naught comma y naught from the set of possible solutions, all possible solutions, to minimize the value of x naught, to minimize the value of x naught. So we are saying out of all the positive integer solutions of the equation, we are selecting a particular solution x naught comma y naught, which minimizes the value of x naught. So now putting that in the original equation, we get equation was x square plus y square plus 1 is equal to xyz, and what we will get is x naught square plus y naught square plus 1 is equal to x naught y naught z, and we'll rewrite it like this. We'll think of it as a quadratic in x. This is my quadratic in x, which has a solution x naught, right? Because you can put x naught for x here in this quadratic and you will get this result. I'm just rearranging it and thinking of it as a one root of the quadratic, x square minus x times yz plus y square plus 1, right? So we get the other root, let's say other root is x1. So x naught plus x1 should be equal to yz, should be equal to y naught z, right? That is by Vieta's relation. So from here, and on the other Vieta's relation is x naught x1 is equal to y naught square plus 1, right? From this equation, we are getting these two relations. X naught and x1 are the two roots. So we can say that the other root x1 is y naught z minus x naught, right? From the first Vieta's relation. The other root x1 is y naught z minus x naught, which is an integer. This is clearly an integer, y naught z minus x naught, right? Now we are going to show that actually these inequalities are true. 0 is less than x1. x1 is the other root, which is equal to y naught square plus 1 by x naught. And since we had assumed that x is greater than y, so x naught was greater than y naught, so obviously x naught is greater than equal to y naught plus 1. So we can write here is less than equal to y naught square plus 1 by y naught plus 1, and that is clearly less than equal to y naught. So what we are getting is that there is another positive integer solution. There is another positive integer solution y naught x1, which satisfies y naught is greater than x1, right? Correct. We are getting y naught is greater than x1, and we know already that y naught is less than x naught. So this implies that x naught is greater than x1. So from the given equation, assuming that we had selected a solution x naught y naught such that x naught was the minimum value, without loss of generality, we had assumed that x naught is greater than y naught. And then when we put it in the original equation, we were able to say that there is another root x1, and that root x1 satisfies x1 is less than y naught. So therefore x1 is less than x naught also. But that contradicts our assumption of the minimality of x naught, right? We had said that this is a solution which was the minimum x naught, and now we are able to construct a new solution y naught x naught x1, where x1 is the minimum. So it is contradicting our assumption of minimality of x naught. Therefore, there are no such solutions where z is not equal to 3, because all of this started when we said z is not equal to 3. So we have x is not equal to y, and we were checking solutions of this form. We are not getting any solutions of this form because we are getting a contradiction. So all the solutions of this equation must be of the form z is equal to 3, right? Now I want to show you a theorem that is sometimes very useful in problems. So this theorem is stated like this: let P be a prime number of the form 4k plus 3, then we can say that x square plus 1 is congruent to 0 mod p has no integer solutions. Has no integer solutions. So basically we are saying that if the prime number p is of the form 4k plus 3, then you can never find an x such that x square plus 1 is divisible by p, or x square plus 1 is congruent to 0 mod p, right? So what this means is for any integer x, a prime factor of x square plus 1 is either 2 or is congruent to 1 mod 4. It can be 4k plus 1, but it cannot be 4k plus 3. It's either 2 is a prime factor of x square plus 1, or if it's an odd prime factor, it cannot be of the form 4k plus 3. Because if x square plus 1 has a prime factor of the form 4k plus 3, then it will be 0 mod 4k plus 3, but that is not allowed according to the theorem, right? So the proof also can be discussed quickly. So this is the proof. You can say, assume that there is an x which satisfies x square plus 1 is congruent to 0 mod p, right? So that means x square is congruent to minus 1 mod p, and if x square is congruent to minus 1 mod p, then x power p minus 1 will be congruent to minus 1 power p minus 1 by 2 mod p. But we know that p does not divide x. P does not divide x. So from Fermat's little theorem, x power p minus 1 should be equal to 1 mod p, should be congruent to 1 mod p. And therefore from here we get 1 should be congruent to minus 1 power p minus 1 by 2 mod p. And this implies that minus 1 is congruent to 1 mod p, and which means p must be 2. So if there is an equation satisfying this, we are getting the prime p must be 2, which is not of the form 4k plus 3. Right? We are assuming that it was of the form 4k plus 3. So we are getting not something not of the form 4k plus 3. So that is a contradiction. And therefore, this there is no x that satisfies this as long as p is of the form 4k plus 3. Basically, what we have shown is if you assume that p is of the form 4k plus 3, x square plus 1 is equal to 0 mod p implies that p must be 2, which is a contradiction. Okay, so how do we use this theorem? Before we do that, we'll write another version of this theorem. So another way to say it is, if p is a prime number of the form 4k plus 3 and integers x and y satisfy x square plus y square is congruent to 0 mod p, then both x and y must be divisible by p. This is saying the theorem in a different way. Earlier we said that if p does not divide x, then x square plus 1 is congruent to 0 mod p has no solutions, right? Now we are saying if x square plus y square is 0 mod p and p is a prime of the form 4k plus 3, then both x and y must be divisible by p. That is just stating the theorem in a different way. Okay, so let's look at a question now which deals with this concept. So we have to prove that the equation y square is equal to x square minus 5 has no integer solutions. Has no integer solutions. So, okay, if x is even, what we can do is take modulo 4 on both sides. Take modulo 4 on both sides. So, if x is even, x square will be 0 mod 4. So, minus 5 is basically minus 1 mod 4. So, right hand side is 3 mod 4. And y square is coming equal to 3 mod 4. But that is not possible because we know that the square of any integer can only be 0 or 1 mod 4. So if x is even, we are getting a contradiction for y. Y square is coming as 3 mod 4. That is not possible. So that means x is odd, right? So the first thing is x is odd and the equation was y square is equal to x cube minus 5. So x is odd, x can be of the form 3 mod 4. So if x is of the form 3 mod 4, x cube minus 5 will be congruent to 27 minus 5, 22. It is congruent to 2 mod 4. And then again, it's a contradiction because we are getting y square is congruent to 2 mod 4, but it can only be 0 or 1 mod 4, right? So x cannot be 3 mod 4, right? So x cannot be 3 mod 4 and x is odd, then hence x must be 1 mod 4, right? So we know x is 1 mod 4. So therefore x square plus x plus 1, that will be 1 plus 1 plus 1, that will be 3 mod 4, right? Why are we thinking of x square plus x plus 1? Because I can factorize this, right? I can factorize this like this, y square is equal to x cube minus 1 minus 4, right? And this will become x minus 1 x square plus x plus 1 minus 4. We will be using that here. Now think about it, x square plus x plus 1 is an odd number of the form 4k plus 3. Any integer that is of the form 4k plus 3 has a prime factor p, which is also 3 mod 4, 4k plus 3. So therefore, now we can write from here, we can write y square plus 4 as x minus 1 x square plus x plus 1. And if you take mod p here on both sides, where p is a prime factor of the form 4k plus 3. P is a prime factor of which number? It is a prime factor of x square plus x plus 1, and it is of the form 4k plus 3. So now we are getting y square plus 4 is congruent to, this is clearly 0 mod p now. And now what we know from this is that we are getting it in the form of the second version of the theorem. We are getting x square plus y square is congruent to 0 mod p, which implies both x and y are divisible by p. So from here we are saying that p divides 2, p should divide 2 and p should divide y. But p divides 2 is a contradiction since p was of the form 4k plus 3. So p cannot divide 2, and therefore we have arrived at a contradiction using the theorem's alternate form, and therefore there must be no solutions, right? So that is one way to do it. Let's look at another question. This is prove that equation y square is equal to x power 5 minus 4 has no integer solutions. Again, here also you can do the same thing. You can try and work it out using the theorem again in the same way. So that approach is still there. You can try exactly the same approach as we did just now, right? However, I will show you this with a different method. We can write it like this: y square is equal to x power 5 minus 4, and take mod 11 on both sides. On both sides. Why mod 11? Because we know from Fermat's theorem that for any integer x, x power 10 will be congruent to 0 or 1 mod 11. Why? Because you will get x power 11, which is the prime, is congruent to x mod 11. This is Fermat's theorem. From here we can conclude this. So x power 10 is congruent to 0 or 1 mod 11. So x power 5 will be congruent to 0 or plus minus 1 mod 11. So if x power 5 is congruent to that, the RHS when you take mod 11 is congruent to minus 4, minus 3 or minus 5 mod 11, right? Basically that is 7, 8, 6 mod 11. That is the possibility for the RHS. Now it is very easy to verify that the LHS mod 11 y square can only be 0, 1, 2, 4, 5, 9 mod 11. It is very easy to verify that. Take y as 0 mod 11. So y square can only be 0. If y is 1 mod 11, y square can only be 1. Y is 2 mod 11, y square will be 4, right? So you check all the possibilities for y square mod 11. You will get y square can only be these, but RHS is coming out to be these, which means that they can never be equal, right? So there must not be any possible integer solutions here. So that concludes this video. I just wanted to show you two, three problems and the theorem, which is quite interesting, and hopefully you will be able to use them in your problems. So what I will be doing is in the course, I'll be sharing a lot of these assignments on number theory. You should try them out. If you are stuck with those assignments, you can reach out to me in the course and I'll get back to you with the solutions. That's all for this video, and this concludes our number theory section for the course. That's it for now. I'll see you next time.